Okay, and share the screen. Okay, can you see the slides at home?
Yes.
Perfect. Oops. Okay, so today we will continue with the second module of the course, and we will start discussing a very important subject, which is the theory of Dirac for relativistic fermions, which was a very successful attempt to translate quantum mechanics in a relativistic framework. Okay, which is exactly what we need, of course. So to correctly describe the dynamics of high-energy elementary particles, we need to adapt the concept of quantum mechanics, of course, but now to the principle of special relativities. So we need to make quantum mechanics invariant under Lorentz transformation, in other words. And this corresponds essentially to require that space and time are treated on the same footing. Okay. So let me start with the Schrodinger equation that you all know very well. So the Schrodinger equation is manifestly not Lorentz invariant because the time and the spatial derivatives appear at different orders. So the time derivative is first order and the spatial derivative is a second order. Okay. So it cannot describe relativistic particles. Okay. So what we need is to find a new equation of motion that describes the dynamic of elementary particles in a Lorentz invariant way. And a first approach was proposed actually even before the Schrodinger equation by Klein and Gordon. So let me now switch to the blackboard and I will try to derive you the Klein-Gordon equation. All right. So in their approach, Klein and Gordon essentially express the standard wave function in, let's say, somehow a Lorentz invariant way. So in terms of the position for momentum x mu. So this we can write first explicitly as x0, x1, x2, x3, or more, even more explicitly as psi c prime minus x minus y minus z. Okay. Then we need, of course, to introduce the operators, okay, to construct our equation. And we do this in actually in perfect similarity with the non-relativistic quantum mechanics. Okay, so we introduce the momentum operator, P mu, now with the Lorentz index mu, okay, which is defined as E h bar in the x mu. Okay, as usual, we move 0, 1, 2, and 3, 0 for the time component, and 1, 2, 3 for the special components, as usual. Okay, so the shape of the operator is just the same we have in standard non-relativistic quantum mechanics, but now it is Lorentz invariant. So let's consider, for instance, the 0 component. So mu equals 0. So the P0 is I h bar in the x0. And x0 is just c times time. So this is I h bar in the c or 1 over c I h bar v in the t. So now we can multiply by c. So the P0 times c, which is nothing less than the energy operator, okay, is just the usual one. So E h bar v in the t. What about the special components? Okay, so of course the special components are given by minus I h bar and the nabla vector that I guess you know already, which is nothing else than the in the x1 in the direction of x1 plus the in x2 in the direction of x2 plus the in x3 in the direction of x3. Okay. So essentially here we have the time derivative in the energy operator, and the three special derivatives, as usual, for the momentum operator. Now, the idea of Klein and Gordon to make a Lorentz invariant equation of motion was to start from the relativistic energy-momentum relation that you know very well. So we start from E is equal to E squared C squared plus M squared C to the fourth. Okay. Let's manipulate this a little bit. So we take the square of this. And we divide by C squared. 1 over C squared. E squared is equal to P squared plus M squared C squared. So this is the starting point to construct the equation. What we have to do now is to replace energy and momentum with the energy operator and the momentum operator, and to make these acting on our wave function. Okay. So this becomes 1 over C squared. Then we have the energy operator, okay, acting on the wave function x mu equal to P squared acting on the wave function. And then we have just the master acting on the wave function. And then we can make explicit now the energy and the momentum operator in this. So I just substitute here, we're going to have minus 1 over C squared H bar squared and the time derivative at the second order acting on a wave function. Then we do the same for the momentum. So this is minus H bar squared, lambda squared acting on a wave function. And then we have the master, which remains checked. And now the last step is just to group all the derivatives all together, okay? Time derivative and the special derivative, we put them all together. So this we can write as 1 over C squared, D squared, and then T squared minus lambda squared, acting on the wave function, plus M squared, C squared, divided by H bar squared. We're going to divide by H bar on X mu is equal to 0. Okay, and this is the Klein-Gordon equation. So the question is this equation now Lorentz invariant? Yes, it is, because now both the time derivative and the special derivative come with the same order. They are both at the second order. Okay, let's now switch the slide. Okay. So I put the question also here on the slide. So since both the spatial and the temporal derivatives of the Klein-Gordon equation are the same order, this equation is now Lorentz invariant. And we can also write it in a more compact way, or even in the explicitly in the covariant form. So what we do is actually to group together the second order derivatives, okay, using now the Lorentz index mu. So this goes from 0 to 3, so this includes the time derivatives and the special derivatives. We put the mass term or inside here, and we can write these even more in a more compact way using this notation here. So the second derivative, okay, we can also write as d mu, with indices in the upper and the lower position. And this is, let's say, the Klein-Gordon equation in a covariant form, where the mu index, of course, spans from 0 to 3. Okay? So now, few comments about this equation. First of all, the Klein-Gordon equation describes the dynamics of free particles with a mass m, which enters here explicitly in the equation, and spin 0. So this equation only works for scalar particles, where scalar means that they come with spin equals 0. Okay? In fact, it cannot describe the dynamics of fermions. We know that fermions come with the same integer spin, so non-zero spin, like leptons and quarks. So you cannot treat the dynamics of leptons and quarks using the Klein-Gordon equation. This is a very strong limitation, but it is not the only one. There are three additional problems here. So the first one is that this equation allows negative energy solutions, which of course are nonsense, and which derive from the fact that we started from this quadratic equation with energy. So here we should expect a positive solution, positive energy solution, and also negative energy solution. And this was the first problem. The second problem, as we will show later on, this drives to the possibility of having negative probability densities, which is nonsense, okay, and which is a consequence of the second order derivative with respect to time. And the last problem, which is also fundamental, is that when you calculate for a particle in an electromagnetic potential, when it is calculated, okay, for the dynamics of a particle in electromagnetic potential, you obtain a value of the fine structure constant, which is completely different than the experimental value, that you know is 1/137 at the low energy scale, okay? So this equation is elegant, is Lorentz invariant, works for scalar particles, but has a lot of problems. Okay. Now, in 1928, actually, let me tell you that, as I was mentioning before, the Klein-Gordon equation was developed and proposed even before the Schrodinger equation. Okay. But nonetheless, Schrodinger became much more famous because the Schrodinger equation works perfectly well, and this guy here works only in some limited cases. Okay, so they lost their chance to be famous. Now, so we have to solve all the problems that I listed in the previous slide, okay? And part of the solution arrived by, were proposed by Dirac in 1928, okay? Who proposed a new Lorentz invariant equation, where now both the spatial and the temporal derivatives are at the first order. And this makes a big difference, okay? So the equation we can write here in the form of an eigenvalue equation. So you recognize here the energy operator, E, okay? And this HD is the so-called Dirac Hamiltonian or Dirac operator, which is a linear function of first order spatial derivatives in this way. So H is given by alpha P, where P is the momentum operator, the usual momentum operator, plus some mass term. Okay, so when we now substitute the expression of the momentum operator, we get here the linear dependence on the first order derivative with respect to the spatial coordinates. Is that clear? Of course, now we have to define what alpha and beta are. So alpha is a vector, a three-component vector, and both alpha and beta are actually 4x4 matrices. And those have to be chosen in such a way to fulfill the relativistic equation, okay, the standard energy momentum equation in relativity. And this is only possible if these alpha and beta matrices fulfill these conditions here. So the square of each of them must be equal to the identity, to the 4x4 identity matrix, okay? And they have to fulfill these anti-commutation relations, so among alphas or among alpha and betas, okay? Of course, there are many possible choices for this alpha and beta, okay? And the common choices is, of course, the simplest one, is to use as beta this 4x4 matrix, where I is the 2x2 identity matrix. So we have two by two blocks here, one and there. And the alpha components, where I goes from 1 to 3, is given by 0, sigma I is 0, where sigma I are the three Pauli matrices that you know already from quantum mechanics, describe the spin of fermions, right? So when we now put explicit the Dirac Hamiltonian, we get the Dirac equation in the explicit form, okay, where now you recognize immediately that the time derivative and the special derivative come with the same order, at the same order. Now, there is, however, a more useful expression of the Dirac equation, which is given in terms of the so-called Dirac matrices, gamma mu, where mu goes from 0 to 3. So these gamma matrices are, of course, related to the alpha and the beta that I presented before in the following way. So the gamma 0 is exactly equal to beta, okay, which is the scalar part, and the gamma I, which are 3, okay, are the product of beta times alpha I. And you see here now the full expression of these four Dirac matrices. Gamma 0, gamma 1, gamma 2, gamma 3. And of course, they have to fulfill some properties in order to be consistent with the requirement on alpha and beta that I presented before. And they fulfill, and the requirements are that gamma 0 squared is the 4×4 identity matrix, and the square of gamma I are minus the 4×4 identity matrix. And they also have to fulfill these anti-commutation rules among them. Okay. So now, let me derive on the blackboard the covariant form of the Dirac equation, which is the form that you define everywhere in textbooks. And the form that we will also be using next. So let me start from the Dirac equation in the full expression, the one I showed before on the slides. So we have I, h bar, on the t side, plus I, h bar, alpha scalar nabla, psi, minus beta m psi equal to 0. Okay? So this is the canonical form where we just put explicitly Dirac Hamiltonian. Now we multiply on the left by the beta matrices. Okay, so what we get is I, h bar beta, the t psi, plus I, h bar beta, and we have the scalar product, nabla psi minus beta squared m psi equal to 0. And now you remember that beta corresponds to gamma 0, and that beta squared is just the identity matrix. So this we can write as I, h bar 0, then in the t psi, plus I, h bar. This guy here becomes now the gamma vector, okay? Beta times alpha, scalar nabla, psi, minus, this is 1, or the identity matrix more correctly, so m psi equal to 0. So this is an equivalent form of the Dirac equation now in terms of the Dirac matrices. Okay, and again we can write this in an even more compact form or explicitly covariant form by merging the derivatives. So the formula we're going to use, that you know already, is that d in the t nabla we can express as d in the x0, that in the xk, where k runs over only the spatial components, so 1, 2, and 3. All right, and this we can write as usual as d in the x mu, where our mu are the Lorentz index, so 0, 1, 2, and 3, or even more compact as the mu. So this symbol here is equivalent to this one here. Okay, and so when we use now this notation, we can write this Dirac equation in the standard covariant form. So I, as a gamma mu, the mu minus m psi equal to 0. Which is a Dirac equation in the Covalent form. Right? Okay, let's come back to the slides. Okay. So I put this in the slide for reference. Okay, so find it here. Now, what about the solutions of the Dirac equation? Okay, so this is now the scope of the rest of our lesson today. So to derive the shape, the form, the explicit form of the solution of the Dirac equation for a free particle. So the point is that dealing with 4x4 matrices, either the alpha, beta, or the gamma, equivalently, the eigenfunction psi that enter into the Dirac equation cannot be a simple a standard wave function, okay? But it must be rather a 4-component column vector that we call spinor. And the reason for the name spinor will be clear next week, okay, at the next lesson. So it is an object like this, okay? So it is essentially a 4-component vector. Now, before going into the solution of the Dirac equation, okay, let me first introduce the concept of adjoint spinor and of adjoint Dirac equation, which are absolutely relevant for the Feynman formalism we will study next, okay? So the adjoint spinor, which we indicated with this bar on top of it, is given by the Hermitian conjugate of the wave function, the spinor, times gamma 0, okay? So we can, yeah, the symbol here, we call it daga, means Hermitian conjugate, so it's the transpose of the complex conjugate, as you know. So we can make it even explicit here. So we take the transpose of the complex conjugate of the spin, we multiply it by gamma 0, and once you do this vector matrix multiplication, you end up with this form here, okay, of the adjoint spinor. So let's now make use of this concept to derive the adjoint Dirac equation. Okay. So let me start again from the Dirac equation in the nominal form, the one we derived before. Okay, so I, gamma 0, the in the t psi plus I, gamma k, the in the x k psi minus m psi equal to 0. And now we take the transpose of this. So let me first list here the ingredients that we will need. So the first ingredient is what the Hermitian conjugate of the spinor means. So this, as you know, is the transpose of the complex conjugate. The second that we need is now when we take the transpose of the derivative terms. Okay, so the transpose of gamma mu the in the x mu psi transpose is equal to that in the x mu psi and then gamma mu. And finally, sorry, I'm wrong here. This is a Hermitian conjugate, it's not the transpose. Sorry about that. This is a Hermitian conjugate, Dirac symbol. This, of course. Okay. And the last one, let me remind you that gamma k, the Hermitian conjugate, is minus gamma k. Okay, so now using these ingredients, let me write down this. So we're going to have minus I, because we take the complex conjugate. So it's the minus sign here, minus I, that in the T, psi daga gamma 0, minus I, that in the X in psi daga minus gamma K, minus M psi daga equal to 0. And we can just adjust here the signs. So this is equivalent, of course, to I, that psi daga in the T, gamma 0, minus I, that psi daga in the xk, gamma k, plus m psi daga equal to 0. Let's now multiply on the right by gamma 0. So we want to get rid of the different sign here. We have a plus sign here, a minus sign here. We want to get rid of this. We want the same sign of the derivative. So we multiply on the right by gamma 0. So this is I, the psi daga in the T, gamma 0, minus I, the psi daga in the xk, gamma k, gamma 0, okay, let's make one more passage, psi daga gamma 0 equal to 0. And now we make use of the anti-commutation relation that gamma k, gamma 0 is equal to minus gamma 0, gamma k. So when you switch the order, you have to change sign here. And so here we recover the plus sign. So we just switch those two here. Okay, so this becomes a 0, this becomes a k, and this becomes plus sign. The last thing we need to remember is the definition of the adjoint spinor. So the adjoint spinor is the Hermitian conjugate gamma 0. And this we have already here. See? So one here, and one here, and one here. So at the end, we can write this as I, that of the adjoint spinor in T, gamma 0, plus I, that of the adjoint spinor in the xk, gamma k, plus m adjoint spinor equal to 0. And this is the adjoint Dirac equation.
Sorry, may I ask a question?
Yeah, sure.
On line 3, I'm not sure I understand why the minus psi, well, from 2 to 3, why is the sign of the mass term change?
Yeah, let me check. You're right.
Because the first one, sorry.
Yes. No, it only changes when we change all the signs altogether. So here we are changing all the signs everywhere, right?
You're changing, yes, and there's the minus.
Minus give a plus, and then we change everything, it becomes a minus, and it becomes a plus.
Okay, sorry, thank you.
That's no problem. Okay. Now, okay. So we are back here. I also put the adjoint Dirac equation on the slide for your reference. Okay. And this, as usual, can also be written in a compact and manifestly covariant form, as usual, okay, by introducing the Lorentz derivatives, where now we have to take care that for the adjoint case, the adjoint spinor is on the left, and so the derivative acts on the left side. Okay. Now, why have we spent so much time for this? Okay, this will be clear, of course, in the next lessons, not everything today, but just let me now make use of both the Dirac equation and the adjoint Dirac equation to derive the continuity equation, the analogous that you know already from quantum mechanics, from non-relativistic quantum mechanics that you can derive from the Schrodinger equation. So if we multiply the Dirac equation on the left by the adjoint spinor and the adjoint Dirac equation on the right by the spinor, and we sum the results, we obtain the continuity equation, let's say the relativistic form of the continuity equation, which is the analogous of the one you obtain from the Schrodinger equation, where rho is, as usual, the probability density, and J is the probability current. So let's make this. Okay, so our starting point is, as usual, the Dirac equation in the canonical form. So gamma 0, that in the t psi plus I gamma k, that in the xk psi minus m psi is equal to 0. Okay. Now we multiply the Dirac equation on the left by the adjoint spinor. So this is going to be I adjoint spinor, and actually 0, then the t psi plus I adjoint spinor gamma mu, gamma k, that in the xk minus adjoint spinor m psi equals to 0. Now we take the adjoint Dirac equation and we multiply on the right by psi. So this is going to be I, then in the t adjoint spinor gamma 0 psi plus I, that in the xk adjoint spinor gamma k psi minus psi bar m psi equal to 0. And we sum the two. Pennarello sta già arrivando alla fine. Okay, so let's now add term by term what we have here. So we have I, then we have psi bar gamma 0, then in the t psi plus that in the t psi bar gamma 0 psi. And it is this plus this. Now we move to the second terms plus I c bar gamma k, that x k psi. We are here plus that in the x k psi bar gamma k psi, and these are the sum of the second terms. And so this is a plus sign here. And indeed, these last two terms drop in the sum. So all this must be equal to 0. So what do we have here inside the parentheses? If you check carefully, we have a function times the derivative of another function. So this is adjoint. and the derivative of the first function times the function. So this is nothing less than the derivative of a product of two functions, right? And the same thing here. So this we can write as, we can also simplify the I here, we don't need it more. So that in the T, adjoint spinor gamma 0 spinor plus that in the xk adjoint spinor gamma k spinor equal to 0. Okay? You can just check that. You take the derivative, you get back to this. Okay? So here. So what is this? So this we can call the rho. So the probability density. This, with the spatial coordinates, is nothing less than the probability current. So it's a vector J, which is the probability current. And so we can write this in a more convenient form as, without, of course, as usual, we merge now the temporal and the spatial derivatives. So as that in the x nu. And then we have psi bar gamma mu psi. Okay. We are now merging these two terms as usual using the Lorentz indices. This is nothing else than the 4 vector current. Okay, this is a 4 vector now because we have 4 components here. So this is that in that x mu j mu, and it is equal to 0. And when we have a derivative equal to 0, this means that the quantity inside is conserved. Okay, it's not changing. So what is the quantity is conserved is our 4 vector current, J mu, which is defined as rho and the 3 vector current, J, as C bar gamma mu C. And this is a constant. Okay, because the derivative vanishes. So clearly, this expression here is nothing less than the Lorentz invariant version of the continuity equation that you see, that you know from non-relativistic quantum mechanics. Okay. There is another important point that I want to make here, and it is about now the probability density. So the probability density is this guy here. So as rho is the 0 component of our 4 current, J0. And so this is psi bar gamma 0 psi. We can now make explicit the definition of the adjoint spinors. So this is the emission conjugate gamma 0 psi. But gamma 0 squared is the identity matrix. So this is nothing else than psi bar psi, which is our standard probability, which is, of course, positively defined always. So let me comment on this on the slide. So this is the result that we got on the blackboard. Okay. So the 4 vector current is a conserved quantity in the Dirac theory. And it also turns out that the probability density is positively defined, always. And this solves one of the problems of the Klein-Gordon equation, if you remember. Because if you now do a similar job on the Klein-Gordon equation, you end up with a probability density of this, with this expression here, where you do have a minus sign here. So this quantity can be positive, but can also be negative. And so nonsense negative values for the probability density are allowed by the Klein-Gordon equation, which is indeed a problem, which is now solved by Dirac. Okay? So the Dirac equation has not this problem. Okay. Suppose that we insert the electron charge in our 4-vector current, then what we obtain here is the so-called electron current density, okay? That will become absolutely extremely useful in the next lesson, so we will see, okay, in QED, and which transforms as a 4-vector under Lorentz transformation, okay? So J is a 4-vector, so it transforms under a Lorentz transformation. Now, this is, of course, a very specific case of current, okay? Of Lorentz invariant current, but there are several other possibilities. So in general, the most general form of the Lorentz invariant currents is expressed in terms of bilinear quantities in this form here, psi bar, then some combination of 4x4 matrices and psi, okay, which is indeed the case of our vector current that we just derived. So here in general, 4x4 means any possible products of the gamma or combinations of the gamma matrices, okay? And the list of possible Lorentz invariant currents is not infinite, okay? There are only 5 possibilities that you find here. So the simplest one is the so-called scalar current, just psi bar psi. Then you have the vector current, which is the one that we just derived, okay, with the gamma mu matrices here. Then we might have also the tensor current, okay, where the sigma mu is a tensor which comes with a kind of combination of the gamma matrices. Then we might have the axial vector current with the gamma mu gamma 5, where gamma 5 is given by this combination of the Dirac matrices. So I, gamma 0, gamma 1, gamma 2, gamma 3. Okay, and this will become absolutely important in the weak interaction as we will study in the next part of the course. Okay, and then one can also have the pseudo-scalar current with the gamma 5 only. So these are the only possible Lorentz invariant currents that one can construct. Okay. Okay, we can make 10 minutes break. Okay, we recombine at 10 past 12. Any questions? So in the next part of the lesson, we will now study the solution of the Dirac equation and try to get also a physical interpretation of them. Okay, let's make a break. See you in 10 minutes. Shall we start? All right. Okay, can you see the slides from remote?
Yes. Yes.
Thank you. Okay, so let's now continue. So we introduced the Dirac equation, which is an attempt to make quantum mechanics Lorentz invariant. Okay, so an equation of motion that works for relativistic particles. We derived also the adjoint Dirac equation. Okay, and we merged together to get the continuity equation. And we introduce also this 4-vector current. So now the next step is to try to solve the Dirac equation and try to derive the solutions, so the eigenstates. And then, of course, to provide a physical interpretation of the solutions. So the solution of the Dirac equation for a free particle, so a not interacting particle, suppose we have no interaction potential, and this very simple approach, is of course a plane wave, but now on a form of a 4-component spinor. Okay, so in general we write it in this way, but we can introduce now the 4-component spinor U, which is a function of energy and momentum, and then we have the standard plane wave, and we can further split the U spinor into two-component spinors, the phi, which is the upper component, and the chi, which is the lower component. Okay, overall we have still 4 components. Now, to extract the functional form of the Dirac spinors, so the solution of the Dirac equation, it is convenient to solve the Dirac equation in the form of the Eigenvalue equation. So let's go back to the original Dirac operator that I showed before, okay? And let's now try to derive the solution out of this. So, the Dirac operator acting upon our eigenstate is expressed as alpha scalar p plus beta m acting on U. Okay, and now we make explicit alpha. Okay, so this is let me go here. So if you remember, alpha is a 4x4 matrix which includes the 2x2 Pauli matrices inside. So this we can write as 0. Then sigma vector, which corresponds to the 3 Pauli matrices. Then sigma vector and 0, scalar p, plus the beta matrix, if you remember, is given in terms of the identity of the 2x2 identity matrix. So this is I, 0, 0, and minus I times the mass. And all these act on our 4-component spinor that we can split into the upper and the lower component. So this is phi. Okay. And this is, now we are writing the Eigenvalue equation, this is E times phi chi. Okay. So this is the energy eigenvalue. So let's make let's make now the sum of these two matrices here. So this is going to be equal to, okay, in the 1, 1 position we have Im plus 0, so this is just M I. In the 1, 2 position we have sigma p plus 0, so sigma p. In the 2, 1 position we have sigma p plus 0. And finally we have minus Im, so minus M I, acting on phi a equal to E phi k. Now we can translate this into a system of equations. Okay, So let's make the product of the matrix with this column vector. So this times this plus this times this. And then we saw on the first line we have mi phi plus sigma dot p chi equal to e phi. And for the second one we have sigma scalar p phi plus minus mi phi equal to e phi. And this we can write in equivalent form. Let's just put this term inside, so we collect the phi term. So this is e minus m I phi minus sigma dot p chi equal to 0 for the first equation, and minus sigma dot p phi plus e minus m I chi equal to 0. So what we can say about this system of equations? So we do see two equations, but each of these is a double equation because we have a two-component spinor. So overall, this is actually a system of 4 equations, and so we expect 4 solutions. The other comment is that we don't have constant term in this equation, so this is a so-called homogeneous system of equations. Okay? And the consequence is that, as we will see in a moment, that the solutions are correlated 2 by 2. Okay? So we have to solve this system, and this system admits solutions when the determinant, the corresponding determinant, is equal to 0. So let's evaluate the determinant here. So E minus M I minus sigma P minus sigma P and E plus MI plus something. Okay, so this determinant must be 0 in order to have a real non-trivial solution from this system of equation. So let's calculate this determinant. So we have E minus M times E plus M I squared from the first diagonal. And then we have minus sigma scalar P, sigma scalar P. And this we want to be equal to 0. Now this really is E squared minus M squared. And this, you can check yourself with simple passages that I will not do, but it's nothing less than T squared. Just make use of the Pauli matrices and take the products. So overall, what we found is that the system admits non-trivial solution if T squared is equal to T squared plus M squared, which is our beloved energy momentum relativistic relation, which is always fulfilled. So this system always admits non-trivial solutions. Ok? Ci siete, ragazzi? Okay, let's go back to the slide now. Okay, now the problem arrives, okay? Because similarly to the case of the Klein-Gordon equation, we still have a quadratic expression in energy, which provides also negative energy solution, okay? So we end up with the same problem that was already encountered by Klein and Gordon at the time, okay? So the Dirac equation provides also solution with negative energy, and we have to deal with this and to find also a physical interpretation to this. So solving the problem, solving the system, one obtained then the 4 solutions. So 2 of them corresponds to positive values of the energy, and the other 2 corresponds to negative value of the energy. Okay. So let's make some comments. All 4 solutions are needed to form a complete set of orthogonal vectors. So the negative energy solution cannot be discarded. We have to take them in hands. We cannot just forget about them. This is the first comment. The second is that, as I was mentioning before, in virtue of the homogeneity of the system, the 2 component spinors, chi and phi, are completely correlated. So you see here, once you fix arbitrarily the chi, you get a value for phi. Once you fix arbitrarily the phi, you get a value for chi, and vice versa. Okay? This is a consequence of the fact that the system is an homogeneous system. And so one can actually choose one of the other arbitrarily. And this is what we're going to do. And in fact, without losing generality, we will choose the solution of phi arbitrarily for the positive energy case, and the solution of chi arbitrarily for the negative energy case. What does it mean? So if you look at the positive energy, we put some arbitrary solution for phi, and we get the corresponding solution for chi. For the negative value, we put some arbitrary solution for chi, and we get the solution for phi. Okay? But what kind of arbitrary choice should we make? This we will see in a moment. So in general, let me write down the full expression of this solution, okay? So again, 2 of those corresponds to positive energy. The other 2 corresponds to negative energy. So we have U1, U2, U3, U4, okay? Each of these is split into a 2-component upper and lower spinor, okay? And now we substitute the solution that we found before. So we take, for instance, for this case, we take an arbitrary choice of phi 1, and we obtain the corresponding results for the chi. We take an arbitrary choice for phi 2, and we have the corresponding results for the chi 2. And opposite for the negative energy solution. So here we take an arbitrary choice for the chi 1, and we get the solution for the phi 1, an arbitrary solution for the chi 2, and we get the solution for the phi 2. Okay? So the question is, what kind of arbitrary choice shall we make? So let's make it the most simple we can think of. Okay? So for 2 positive energy solutions, the simplest orthogonal choices for the phi 1 and phi 2, to plug here, 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 and here, are just 1, 0, and 0, 1. Okay? There is nothing more simple than this. So let's now put this into our solution and see what we get. So let me concentrate on the first positive energy solution, U1. Okay. So as an arbitrary choice for the phi 1, we take 1, 0. And for phi 2, we take 0, 1. Okay. And let's now substitute this into the equation. So we have U1 is equal to some normalization coefficient of phi 1 chi 1. That is n1 phi 1, and the solution we found is sigma times p divided by e plus m phi 1. Let's now make explicit this scalar product here. So this is n1. So here we have 1, 0. Now 1 divided by e plus n that multiplies sigma 1 px, this is just a start of, plus sigma 2 py plus sigma 3 pz acting on 1, 0. Okay. Let's now put even more explicitly the Pauli matrices here. So this is N1 that multiplies. So we're going to have 1, 0 as the first component, and then 1 divided by E plus M. So we multiply now Px with the first Pauli matrices. And this is 0 Px, Px 0 plus, now on the second Pauli matrices, 0 minus I py 0 plus pz 0, 0 minus pz acting on 1, 0. Now we make the sum of all these matrices here. So this is N1, then we have 1, 0, 1 over E plus M that multiplies. So we have 0 plus PZ. So this is just PZ. Then we have Px minus IPy plus 0. So we have Px minus IPy. Then we have Px plus IPy plus 0. And finally, we have minus PZ plus 0. Now we make this matrix vector product. Okay. So we end up with N1, 1, 0, 1 over P plus M. So now we multiply this row with 2 times 1 and this row times 0. So we're just going to have PZ and Px plus I Py. And so the last passage is just writing these as a 4-component spinner. So we have 0 for the first component, sorry, we have 1 for the first component, 0 for the second component. Then we have Pz divided by E plus M for the third component, and Px plus I Py divided by E plus M for the third component. This is our spinner. This is U1. One can do the same exercise for U2, of course. Let me just give you the solution. We will not go through again the passages. And so, acting the same way, so this is U1 for U2, you would find N2 by 2 by 2, and this can be equal to N2 by 2, and the solution, which is sigma dot P divided by E plus n by 2. Okay, we put our arbitrary choice for phi 2, which is 0, 1, if you remember. And so at the end, after the same algebra, we end up with n2, 0, 1, px minus phi py divided by e plus m, and minus pz divided by e plus m. Okay. Let's go back to the slide now. So let me summarize on the slide what we just found. Okay, with the only difference that we now make explicit this normalization coefficient, okay, which turns out to be equal to square root of E plus M. So these are the first two solutions corresponding to the positive energy case, okay. Then, of course, we have to deal with the two negative energy solutions, okay, the other two, okay. In this case, as I was mentioning before, we take arbitrarily the choice for the K1 and the K2, and we solve for phi, okay. That's the opposite choice. Everything is arbitrary here. This is just what is commonly done. And once you do that and you do the same algebra, you obtain now this expression for the U3 and the U4, okay. So now we have the full set of solution of the Dirac equation. Two are positive energy solutions, the other two are negative energy solutions. And so the question is now, how can we physically interpret this negative energy solution? Okay. So when Dirac arrived to this negative energy solution problem, people was very skeptical about the Dirac theory. Okay, it must be wrong. But Dirac was really convinced that the theory was correct, and so he found out a way to interpret this solution and to convince people. And the outcome of this interpretation was finally confirmed by the experiment, as I will show in a moment. Okay, but it was at the end an extreme success of the theory. So how to interpret the negative energy solution? So Dirac introduced a new concept of vacuum. So the vacuum is a state in which all infinite negative energy levels are occupied by electrons in accordance with the Pauli exclusion principle. Okay, so you see here all the negative infinite, so you go up to down to minus infinite here, all the negative energy states are occupied by 2 electrons, and only 2 because of the Pauli exclusion principle. Okay, either 1 or 2, no more than 2. Now, all the positive energy levels are empty in this new concept of the vacuum, okay? And of course, the Pauli principle prevents positive energy particles to collapse into negative energy levels because they are all occupied. Cannot happen. So this is what Dirac considered the vacuum. Now, of course, one can create a hole in the negative energy level, so in the so-called electron C, okay? How? By exciting a negative energy electron to a positive energy state, okay? You cannot do vice versa, but for sure you can do in this direction because all the positive energy states are empty. And so you need essentially an energy gap of twice the mass of the electron in order to make this jump possible. So suppose now that indeed a photon with an energy equal to twice the mass of the electron hits the electron in the highest negative energy level, okay? Then the electron absorbs the energy from the photon, and now the quantum jump is possible. Okay, so the electron will jump to the lowest positive energy level with an energy plus MEC. But now what we have here? So we have now a hole in the Dirac sea, right? So the hole left by the electron in the negative energy level, or in other words, the absence of a negative charge with negative energy, can be reinterpreted as the appearance of a positively charged particle with a positive energy and the same mass of the electron. So the idea of Dirac was that there must exist a partner of the electron, which is exactly the same, but with opposite charge, and of course, positive energy. And this was the prediction by Dirac of the positron, that, as you know, is the antiparticle of the electron. And of course, more in general, Dirac introduced the concept of antiparticles and so of antimatter. It was, of course, an incredible view he had. Now, with this new concept of vacuum, Dirac actually not only predicted the existence of antiparticles, but also the occurrence of the gamma to E plus E minus per production process that was not observed at that time yet. So now, okay, he was very smart. He made a very elegant theory. He also provided some kind of explanation, but clearly everything drops out if we don't have an experimental proof of this, okay? So the question is now to find experimentally the existence of antiparticles, and this will prove the theory, of course. So how this happened? So we are now in 1932, so just 4 years later of the Dirac equation. And while studying cosmic rays, showers, with a cloud chamber in a 1.5 Tesla magnetic field, Anderson noticed some strange charge tracks in his detector. So you know what a cloud chamber is? Okay. So you see here, this is an example of one of these strange appearance in the detector. Consider that we have a magnetic field which is transverse to the slides. So of course, the magnetic field acts to the charged particle through the Lorentz force. Okay. So as you know, of course, it bends the trajectory of the charged particle. Okay. So the question is, how can we interpret now this kind of tracks here? There were more than one. Okay. This is just an example, okay? So this is compatible with, for instance, a positive particle from the top to the bottom, which moves in counterclockwise verse, okay? So given the direction of the magnetic field, you can interpret this track due to a positive particle coming from the top to the bottom. Now, what I mean by top and bottom? So this experiment was launched with a balloon in the atmosphere, okay? So top means coming from the space, bottom coming from the Earth. However, you can interpret the same track in an opposite way. So you're also gonna have this kind of track for negative particle now coming from the bottom and moving clockwise. There is no way to distinguish between the two possibilities, okay? Now, the curvature and the concavity of the tracks were indeed compatible either with a negative particle coming from the bottom in a clockwise direction, or with a positive particle coming from the top counterclockwise, okay? So at that time, 1932, the only known charged particle were the electron and the proton. Okay? All the rest was discovered, of course, later. And by studying the features of the tracks, so essentially the thickness of the track in the cloud chamber, it was pretty clear that the track was compatible with a charged particle with the mass of the electron. So it could not be a proton. The feature of the track for the proton would be completely different than the one they observed. Okay? So everything seemed to indicate the passage of an electron from bottom to top. And now the question is, where does this electron come from? Because we are studying cosmic showers, so it should come from the top to the bottom, not from the bottom to the top. Okay. So Henderson had the idea to find a solution to disentangle this up-down ambiguity. So what he did was to put a layer of lead, okay, in between his detector. And you know that when a charged particle goes through some material, it loses energies. And if it doesn't lose energy under the magnetic field, it will bend more. So indeed, what you see here is that the bending of the track is enhanced after the passage of the lead layer. So by sure, this particle was coming from the top to the bottom. Was coming from the top to the bottom, was slowing down here, and then was increasing his curvature after the lead layer. Clear? So we can get rid of these negative particles coming from the bottom, okay? And the solution, of course, is that this must be a positively charged particle coming from the top and with the mass of the electron. So this was indeed the discovery of the positron. The first antiparticle ever discovered, as predicted by Dirac 4 years later, okay, before. And the following year, so it was 1933, using an improved version of the original cloud chamber, Brackett and Occhialini, so in a different experiment, not only confirmed the discovery of the boson, but also discovered the E plus E minus per production process. It was also predicted by Dirac in 1928. Okay, so now the theory has a solid experimental background, endorsement. Now, what we can say today about antiparticles, okay? So today it is an experimentally established fact that each fundamental fermion, for each fundamental fermion there exists a counterpart of antimatter, so an antiparticle. So antiparticles have opposite electric charge with respect to their corresponding particle, but they propagate forward in time and with the positive energy, just like particles, okay? Furthermore, they ionize the gas in the tracking detector, just like particles. They produce electromagnetic shower in calorimeters, just like particles, okay? And they undergo the same interactions as particles, okay? Gravity, electromagnetic, weak, and strong. So, of course, it is not straightforward to reconcile all these observations with the negative energy solution that emerged from the Dirac theory, okay? And in fact, today, the Dirac picture is, of the vacuum is only of historical interest, because it provides, some fundamental difficulties. First of all, we know that we have also anti-bosons, so antiparticle bosons, but for bosons, the Pauli principle does not work. So the Dirac theory cannot explain the existence of anti-bosons. And also, we have a fully occupied negative energy vacuum, okay? And this, of course, corresponds to an infinite energy, which you cannot explain physically, okay? So the idea was good, it was endorsed by experiment, but also here we have some problem, okay? So we have to interpret this negative energy solution in a smarter way, in a more modern way, and this is the so-called Feynman-Stackelberg interpretation. So according to the Feynman-Stackelberg interpretation, the negative energy solution corresponds to unphysical negative energy particle propagating backward in time. Okay, so it's just a mathematical result, but without physical meaning. However, if you now look at the time dependence of the wave function, which is the usual exponential, okay, you realize that this remains unchanged under the simultaneous transformation of e to minus e and t to minus t, of course. Okay, so in this Feynman-Stackelberg interpretation, these unphysical negative energy particles propagating backward in time, this is the time direction, okay, can be reinterpreted now as physical positive energy antiparticle with opposite charge and propagating forward in time, okay? So from the mathematical point of view, there is no difference. From the physical point of view, there is an immense difference, of course, okay? Now, back to the Dirac solution. Okay, so following the Feynman-Stackelberg interpretation, the unphysical negative energy particle spinors U3 and U4, okay, can now be rewritten in terms of physical positive energy antiparticle spinors. So we have to introduce a new symbol here, which is V, V1, and V2, and V3 and V4 as well. Okay, so the U are the antiparticle spinors, 2 with positive energy, 2 with negative energy, but we're going to have also 4 antiparticle spinors, again, 2 with positive energy and 2 with negative energies. And for instance, you can get the V1 and V2 solution just starting from the U4 and U3 and exchanging the sign of energy and momentum. But there is a more formal way to get this result, which is to solve again from scratch the Dirac equation, but now looking for solution of this type. Okay, well, now we have the V spinor here, and the momentum and energy are simultaneously inverted in sign. Okay, so once you now do all the algebra we did before the blackboard, but now requiring for this kind of solution, you obtain these 4 new solutions for antiparticles: V1, V2, V3, V4. Again, the first 2 corresponds to positive energy, so they are physical. The other 2 corresponds to negative energy, so they are unphysical. So in total, we have 8 different solutions of the Dirac equation, the 4 U and the 4 B's. Okay, although of course only 4 are independent, because if you remember, we have a system of 4 equations. So the U1, U2, and V1, V2 are particle and antiparticle solutions for positive energy, and U3, U4, V3, V4 are particle and antiparticle solutions for negative energy. Okay. From the formal point of view, from the mathematical point of view, you just take 4 of them and you're done. Okay. only for independent. Of course, from the physical point of view, it makes much more sense to work with the positive energy solutions, okay, corresponding to physical particles and antiparticles. So from now on, through the end of the course, we will only consider U1, U2, B1, B2, okay? And we will neglect the non-physical solution. So now we have understood the distinction between particle and antiparticle solutions. So we have found an interpretation of the positive and negative energy solution. But why do we have two positive and two negative degenerate solutions? Suspense. We will see next time, next week. Okay. So next week next lesson we will continue answering this question and completing the physical interpretation of the Dirac solutions. Okay. Any questions?
Well, so, sorry, I was going to ask, but it's probably linked to what we're going to discuss next week. I just was wondering about the dimension 4 and the number of parameters in the end, the number of degrees of freedom. I'm a bit confused.
So what do you mean? So we have 4 equations, 4 solutions, independent solution. What is the?
So, but he. I'll listen next time. I need to think to formalize.
Okay. So what we will learn in the next lesson is how to solve the degeneracy between the two particle solution and the two antiparticle solutions. Okay, we need to search for a good quantum numbers that allow to distinguish the two. Okay. Then see you next week. In case the pandemic situation gets worse, so we might get here a full red zone, we will continue from remote. Okay, I will now interrupt the registration.